In this video we're going to look at some different complex relations, or I guess complex equations, and think about what their graphs might look like in the complex plane. And to do this I think we'll sort of jump straight in, think of a few, or take a look at a few examples and try and consider some sort of ones that are a little bit different. So what we're doing here in the exercise is illustrating on an Argand diagram, or sometimes the instruction will be to sketch on the complex plane. Might even say show the subset of the complex plane that's represented by an equation. But in this case we've got the equation or expression or relation that 2 times the imaginary component of z is equal to the real component of z, the real part of z. So what we're looking here for is every complex number, every number in the complex plane which satisfies that relation, that 2 times its imaginary part is equal to its real part. And if we were to let z equal x plus yi, we could turn it into an expression or a relation we'd be a bit more familiar with. So 2 times the imaginary part of z would be 2y, and the real part of z would be x. So that's the equation 2y equals x, or y equals a half x. And that's certainly an equation that we're familiar with, and if we think of, well, you know, the x being the real part of z, so real component of z here, imaginary, and those are the x and y. Well, if y equals a half x, that's just what a line passing through the origin with a gradient of a half. So probably something like that. Let's write on the equation of that line there, 2 times imaginary part of z is equal to real part of z. Alright, so sometimes we can just substitute in with x plus yi, and that will sort of give us an understanding there. Let's go one here that's a little bit more complex. So we've got the modulus of z take away, whoops, a daisy, modulus of z take away, what is it, 1 plus root 3i is equal to 2. Alright, so let's first of all take the same approach as above, but then this one will establish a more general pattern for us. So let's let z be equal to x plus yi, because then we might be able to get a Cartesian equation which makes a bit more sense to us. So then we're going to have x plus yi minus 1 plus root 3i, the modulus of that is equal to 2. Well, let's separate this into its real and imaginary part. So its real part would be x minus 1, and its imaginary part would be y minus root 3. And so then we know the modulus is equal to the square root of the square of the real part plus the square of the imaginary part. So that's our rule, or our result for finding modulus. And if we square both sides, well, that gets rid of the square root on the left-hand side. And what we have there is hopefully an equation that looks pretty familiar. What's that one? That's a circle, center at 1 root 3, and radius of 2. So let's have a go at sketching that one. And alright, let's center that here. So its center is the point, what do we say, 1 and root 3. So the y-axis should be, what, 1 unit to the left of that, shouldn't it? Or when I say y-axis, I really mean imaginary axis this case. And root 3 will be a little bit further above the real axis. So there it is, a circle, center 1 root 3 and radius of 2. Now we can generalize this one and say, in general, when we get something of the form z, take away some complex number, so we'll just call it the complex number z1. So in this case, z1 was 1 plus root 3i. If we get the modulus of that being equal to k, then that produces a circle, with its center at z1 and a radius of k. Okay, let's do a third one with a little bit more complexity. And this one certainly is ramping things up a little bit. So we're using set notation here, and we've got 2 of them. And this one's asking us to sketch the region of the complex plane, or regions of the complex plane, that are represented by this relation here. So, first of all, let's make sure we understand this notation. It's saying we want the set of all complex numbers z such that the modulus of z is greater than or equal to 2 and less than or equal to 3. And then we want to consider the set of all complex numbers z such that the argument of z is greater than pi on 4 and less than or equal to 3 pi on 4. So what we'll do is sketch that one and then sketch this one separately, and then we'll try combining them to get the intersection of those two. Alright, first of all, what does this equation here represent? Well, it's saying we want the modulus of z to be less than that and greater than that. So from over here, we know if we've got mod z minus some number equals some other number, that's going to produce a circle. So here we're saying the center is the origin because it's z minus 0. And so what we end up with is that if we draw a circle, so let's go that circle and let's maybe duplicate that to produce a smaller. Alright, they're not very concentric at that point, are they? We sort of want them to have the same center. So let's draw our axis and our other axis. We want that one up a little bit, don't we? Okay, something more like that. So there's our real and imaginary axes. So what we're saying is we need all complex numbers z whose modulus, in other words, whose distance from the origin, is greater than or equal to 2 and less than or equal to 3. So if this is a circle of radius 2 and this is a circle of radius 3, then it's going to be all the points around in that region, including the points on this line and this line, because it's got the equals 2 as well on the sort of greater than or equals. So if I could shade in this area here, doing a fairly rough job of that, but shading that in, and let's say this is, radius 3, this one's radius 2, 3, 2, so negative 3, negative 2, negative 2, and negative 3. Alright, so that one there is demonstrating, let's use yellow for this one. This is 2 less than or equal mod z less than or equal to 3. Alright, what about our other one over here? So we want all complex numbers whose argument is greater than pi on 4, but less than or equal to 3 pi on 4. Alright, well, I don't think that one's too tricky, is it? Let's think about all complex numbers which sort of satisfy those conditions there. So here's our real axis, our imaginary axis, and we're saying the argument has to be greater than pi on 4, but notice it's not greater than or equal to pi on 4. So this time I'm going to draw a sort of dotted line at pi on 4 there, just to indicate that points along that line are not included. And at the other end, its argument has to be less than or equal to 3 pi on 4. So 3 pi on 4 would be this line around here, wouldn't it? So that's 3 pi on 4 there. And so anything within that region there, let's use green for this one here. So we're saying anything in there, including the line on the left-hand side, the one at 3 pi and 4. So including anything along this line, but not including anything along that line. Any of those points satisfy the statement that argz, principal argument of the complex number, is greater than pi on 4, less than or equal to 3 pi on 4. So we've done those two, and now our task is to say, well, what happens when we consider the intersection of those two sets? So we need z that satisfies that and that at the same time. So if you were to sort of take this one here and slide it over and superimpose it on here, then we'd be interested in the bits where the shading intersects. And so we'd basically have this region of this ring in between pi on 4 and 3 pi on 4. That would be the bit where the two sort of intersect. So can we try and do a little sketch of that down here? Real and imaginary. We'll go with there's our pi on 4. Here's our 3 pi on 4. And so basically we're going to have this, I don't know whether I'll do too well with my rings around here. Something like that, where, let me pick a different color, where that's the common intersection between them. And let's put some numbers on here. So that's 2 and that's 3. That's pi on 4, and that one's 3 pi on 4. And that one there in orange is in fact the one that we're after. So let's label that one as z, where the modulus of z lies between 2 and 3 inclusive, intersection with the set z, where the principal argument of z is greater than pi on 4 and less than or equal to 3 pi on 4.